Okay, good. Now we are recording. That's October the 20th, 10:05 a.m. today. As I mentioned to you before, we are having this AWS incident, the Amazon Web Services incident that's affecting the Canvas and the Zoom services of the district. Because I don't use the Zoom service of the district, but I use my own private Zoom service. It's this link here is not affecting us. Okay, this link here is not affecting us. So one more student joined us. That's good. 1, 2, 3, 4. I presume iPhone should be Princess. Is that right, Princess? You are the one with the iPhone handle. Stream. Okay, Trin. Okay, good to know. Okay, good to know, Trin. Princess was here, but for some reason she left. I do not know if there is any disruption. I want to hear from you, from Edith and Trin. Did you have any problems accessing the Zoom link of the class?
Um, Somebody sent the Zoom link, so I wasn't able to join through Canvas.
Uh-huh. Okay. Okay, thank you. Jason is asking me to send. Okay, I will do that. Good points, Jason. Let me see here. Da, 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 da. I wonder, how this incident occurred. It's very unusual, right, for us to be without internet service. Very unusual. Internet service seems to be far more reliable than even the electricity that we get at home, right? We go without electricity service more frequently than without internet service. Okay, so let me send this link to everybody. Thank you for letting me know, Jason. And let's see, my scheduled class roster. Okay. Notify our students. Okay. Link for today class meeting. Class meeting. Yeah. Class. Okay. Meeting with of yours. It's nothing. It's a link. This is the link. Your personal Zoom account. It's being affected the AWS incident. Really. Send notification. Okay, one more student. Okay, joining us. That's good. Okay, so let's start now. And last time we start talking about the Newton's third law of motion, and we already recording. I'm gonna share my screen. Here you go. Is that the one? Yeah. Let's see. There's some new. Let's see some messages here. I couldn't access from Canvas. I had to go to the email. Yeah. Okay. Yeah, that's right. We cannot access. That's right. The Canvas services is being affected by this disruption trend, and nobody has been able to log into Canvas. I myself was not being able to log into Canvas. Okay, but I keep all my links and important documentation on my own hard drive, in case that there is a problem with the cloud or internet access. Okay, so and Jason was very helpful because he told me to email you all folks the link for the class meeting. Okay, and I did that. That was very thoughtful of Jason. Thank you, Jason. Okay. And like I said, it's just the Zoom, the district Canvas and the district Zoom services that are being affected. The email service is not being affected. The email service of the district is working well, fine, right? And it's amazing how the services of a private company like Amazon can affect, right, the other internet services elsewhere, right? I was surprised. I was surprised to learn that the web services of Amazon is affecting the district, right? And maybe it's affecting some other places as well. I was surprised to know that. Okay, so let's. Am I sharing the screen? Yeah, I'm sharing the screen right now, right? So let's go here to the bottom. Today is the 20th of October. And let's take a look at the syllabus. Here we go. The schedule, right? Here's the schedule of classes. We didn't have any classes on Wednesday. Like I said, I had to take my day off because I had a court appearance. And everything went fine. No problems for doing that. And now let's see. Today is Monday, 20th of October, laws of motion. We are talking about the laws of motion, and we cover all the laws of motion. Now we are doing just some examples for you to become familiar how you can apply those laws of motions. Okay, that's what we're doing right now. And what are we going to do? We're going to do an example of Newton's third law of motion. That's what we're going to do right now. Okay, is the example that I'm going to provide. Here we go. We are going to solve a problem using Newton's second and third laws of motion. And I'm going to formulate this example. It's very important that we do examples, right? So you can understand in practice what those laws really mean, okay? So that's why it's important, again, for you folks to do as many problems as you can, especially examples. Okay, so let two masses, M1 and M2, sit on an horizontal frictionless surface. Oh. A non-force F is applied along the horizontal direction. See illustration. Find. Let's say let two known masses M1 and M2 touching each other, right? Touching each other. Sit on a horizontal frictionless surface. A non-force F is applied along the horizontal direction on mass 1. Okay, see illustration. Find the acceleration of the two masses using, and that's very important here, both masses as the system. I'm going to clarify what do I mean by using both masses as the system. Find using, here you go. Find what else? The force that mass 1 applies on mass 2 applies on 2, and vice versa, right? And 2 applies to 1. Using mass 2 alone as the system, verify the acceleration found in the first item by using mass 1 alone as your system. and applying Newton's third law along the way, okay? So here you go. The situation is, the illustration is like that. Here you go. That is the situation, mass 1 and 2. We are applying a force on mass 1. Mass 1 is behind mass 2. And the whole set, is going to move, okay? I'm going to copy and paste that. Go. Copy and paste. Here you go. That's the illustration that you should be aware of so you can solve the problem. It's the illustration, okay? So let's start with item 1, item I. So using both masses as the system, okay, very important. What do I mean about that, okay? You're going to understand right now what I mean about that, before we start solving the problem, before we start solving this problem, I want to point out, right, that there are 3 different ways of solving. Let's see. I want to point out that there are 3 different, no, not 3 different ways, but 3 different free body diagrams that we can use to solve this problem, okay? 3 different free body diagrams. We have 3 different free body diagrams because we have 2 different masses here, okay? That's why, that's why we have to worry about what is the system. What system, right? What system we are considering? What system we are considering? We are considering in the solution of this problem, okay? We're not solving yet. We are just making a little introduction before the solution of this problem. And it's very important that you understand that, okay? In the first item, in the first item, for instance, right? In the first item, we were asked to use both masses as the system, right? As the system. What does it mean? Well, it means that, and I want you to be familiar with this. By using the 2 masses as the system, it's just by drawing a box around those 2 masses and consider the force applied to those 2 masses. It is as though as the 2 masses behave like a single one, okay? That's what I mean by the 2 masses are the system, are a single system, okay? That's what I mean. The first time, for example, we are asked to use both masses as the system. In other words, the 2 masses should be considered a single object, okay? That's what it means, okay? For this reason, we must consider only the forces applied to this specific system, okay? And the way to do that is by drawing a box around the 2 masses. Remember, this is a frictionless system, okay? It is as though, here you go, a specific system as shown below. Here you go. As shown below. And we do that by drawing a box around these two masses, okay? Okay. The system can also be illustrated in the following way, okay? There's a more obvious way of illustrating the system. Okay, instead of drawing like that, we could draw like that. Can you see that? Right? There is no line here in the vertical. Here I'm emphasizing that this is a single object, that the two masses are behaving as a single object. And I can go ahead and let me do something else here. Here you go. Here you go. I'm gonna take away this guy here. Play the movie, right? Play the movie. Here you go. This external force is being applied, right? It's being applied to this mass. And then we go ahead and draw each of the forces being applied to this object. And finally, you go, this one here. Not just the weight, not just the summation of the two weights, but the summation of the two normals applied to the single object. Here you go. Let's play the movie again. Friction is negligible. If we consider those two masses as a single one, we can emphasize that by drawing a box around it, the two masses. And don't forget also to add the acceleration, right? Because this force is creating an acceleration to the right side. And I'm going to emphasize even more by eliminating this line here. So it becomes more obvious, right? That what you have is, in reality, is being treated in reality as a single object. Not that is in reality a single object, but is being treated as a single object. Being treated as a single object, okay? And when we treat that as a single object, the forces that are being applied to the single object is going to be the weight of one plus the weight of two, and the normal of one plus the normal of two, okay? That would be the first item. And what about the other? We didn't solve the problem yet. I'm just making a brief introduction before we solve the actual problem, okay? So what about the second item, right? In the second item, I am asking you to consider just the mass 2 alone as the system. Okay, we can do that in physics, provided you do it in the right way, right? And how do we do that? We repeat the same thing, but emphasizing just the, let's see, this one. Let's see. I'm going to invert the, I'll make it. The order here is switched. Okay, let me take, let me invert the order there in the problem. Let me invert the order there in the problem, in the formulation of the problem. Okay, so here you go. The force that one applies on two, the acceleration of the two masses using both masses of the system. Find the force that two applies on one, that mass two applies on mass one, using mass one alone as the system, okay? I just want to make it consistent with the drawings there. Verify the acceleration you found in the first item by using mass 2 alone as your system, okay? So let's see, item number 2, illustration of item number 2 is going to be like that, okay? we are going to use mass 1 as our system, and we consider that mass 2 is not there, is not around, okay? And that's how we draw it. And don't forget also we have to draw a box around mass 1, right? And when we draw the box around mass 1, what else does it happen? You have to consider all the forces that are being applied to mass 1. Okay? All the forces, because this mass 1 is being pushed towards mass 2, there will be a contact force between them. There will be a normal force between them. Mass 1 will interact with mass 2, and consequently, mass 2 will interact with mass 1. So now we can start considering what are the forces that are being applied to mass 1. One of them is the force of 2 in 1. Okay? You don't have to worry about the force of 1 in 2 because we are considering only the mass 1 as our system. That's why I dashed my force here. Okay? That's why I dashed my force here. So what else? We must have one more force here, right? 2 more forces applied to mass 1. 2 more forces applied to mass 1. And here you go. One of them is going to be that force that will always be there, the weight. Right? Here you go, the weight. And finally, the normal. And I'm going to put that in different colors so they don't get mixed up, right? Here you go. Like that. Better, right? I'm going to put it on the side. Did you get the idea? That's another free body diagram that we can come up with to solve this problem. Okay? And finally, we have the third free body diagram. Let me just copy this one as well. Here we go. Let me copy this free body diagram as well. For item 2, right? Hey, I didn't. Okay, item 2, you go. The free body diagram will look like that. Don't underestimate those simple drawings, okay? They're very powerful because they can represent actual equations. And I'm going to copy that other one that I didn't copy before, which is this one here. Like that, right? The system can also be illustrated in the following way. This one that you see right in here and the previous one are the same free body diagrams, okay? What you see right in here is the same free body diagram as what you see right in here. Those, let's see, I can put those at the same, oh. Yeah, same screen, right? Yeah, here you go. Those 2 free body diagrams that you see here are the same free body diagrams. The only difference is that this one here is emphasizing the fact that mass 1 and mass 2 are being treated as a single object. That's for item 1. For item 2 is something like that, right? My system is mass number 1. Note, see that M2 was drawn as though it is a ghost, right? Just drawn as a dashed line for a reason. And then we have this other free body diagram. This is just remember, this is just a summary, an introduction, a brief introduction before we solve the actual problem, okay? Here you go. And that's the other one here. the other free body diagram. Okay, so here we go. The forces acting in mass number 2. Huh. Yeah. Let me send to back. Oh no, this one should go to back. Yeah, good. Should be dashed, right? Like I did before. Let's see. Yeah, I dashed here, right? Yeah, let's leave it solid. Okay, that's the box, right? Emphasizing that my system is mass number 2. And I am going to show the forces one by one. Force of 1 applied to 2. Okay. The weight of 2. All the forces being applied to. That's what I mean by making each of the masses separately as a system. Okay. And I'm going to copy. And note, see that this force here, since this force here is not in direct contact with mass number 2, it is as though as this force doesn't exist. 2 either, right? It is as though, that's why I dashed it. And mass 1, that's why I dashed 2. It is as though mass 1 doesn't exist, since it's not part of our system. And now I'm going to copy that. That's a technique that we use to solve this problem, and it works very well, not just for this problem, but for other problems. Item 3, right? Here you go. I'm going to put a comment here. Masses 1 and 2 as a single system, right? Just mass 1 as my physical system, let's put it this way. Just mass 1 treated as my system. Okay, just mass 2. Just mass 2 treated as my system, like that. Note C that the external force F is dashed because it is not in contact with the system, right? It is as though as force F did not exist in the system, like that. So now I'm going to write down something very important, very important. Let's increase the size. Here we go. Each of this, each of these, right, should be the plural, these figures can be used to derive an equation to solve our system. That's the little secret about this free body diagram, okay? That's the little secret. That's the little secret of our free body diagram. Each free body diagram can be used to determine one or more equations. Okay, it's not just one, but especially if the problem is two-dimensional, it can be two equations or more equations. Okay, one equation if the problem if the problem is a 1D problem, comma, two equations if the problem is 2D, is in two dimension, right? And three equations for a 3D problem. Okay, so here we go. And now, with this brief introduction, did you understand the importance of isolating each component, each object, you know, just to produce different equations that can be used to solve your problem? At this point in time, for item number 1, what we want just to find the acceleration of the system, okay? And just to find the acceleration of the system, we can consider the two masses as being a single one, okay? And item 1, right? We got the system. So here you go. So all you have to do is to come up with Newton's second law of motion. In this problem, this item 1, I didn't have to use Newton's third law of motion. In this problem, in this item 1, all we use is Newton's second law of motion. Using Newton's second law of motion, we can find the acceleration of the system. Okay? Remember, this equation is a two-dimensional equation, right? Is a two-dimensional equation. Let's see, I don't want this illustration. I want the other one. Yeah, let me get the other one so we can have all the forces there illustrated, right? Here you go. That's one that we want. I want this one here as well, so we can see all the forces. Okay, so here you go. Here you go. Free body diagram. Free body diagram showing all forces applied to the system. Okay. Don't underestimate this problem. Okay, this is a difficult problem. It's very. I remember having problems when I was a student. I remember having problems understanding the solution of this problem, just because of Newton's third law of motion. I could understand this part here. This part I could understand, but I couldn't. I was not able, as a student. I was not able to understand the other two cases. Okay, and I kept on making mistakes over and over again to solve a problem like that. Okay, so net force is equal to mass of your system. Mass of your system is mass of 1 plus mass of 2 times the acceleration. But let's not forget that this net force is all the forces that are acting in the system, right? And all the forces acting in the system is going to be what? The applied force F plus the weight, the net weight, right? The net weight, I'll call that the net weight, plus the net normal. Okay? Net normal. And by the way, the net weight and the net normal, remember, this is a vectorial equation, right? Because this is a vectorial equation, so we have here in this equation two scalar equations, okay? The net weight is going to be W1 plus W2. And the net normal is going to be normal 1 plus normal 2, right? But those four forces here have only vertical components. This force have only horizontal component. Consequently, the acceleration must be only in the horizontal direction. Okay? So if you were to break it down in the two components, remember that I told you this free body diagram may result in more than one equation, right? Here you go. One is along the x direction, the other is along the y direction. But since there is no acceleration along the y direction, the acceleration along the y direction must be 0. And now we are ready to solve the problem. We want to solve this problem here. We want to solve for this value here, okay? And I'm going to do something else too. Instead of just putting m1 plus m2ax, I'm going to put m1 plus m2a, right? Because the acceleration has only an x component. Okay? Even better, I'm going to put it on the extreme right. Okay? I'm going to do something else too. Here you go. I'm going to simplify what you have here. Like that. And I'm going to simplify what I have here. Right? Like that. But we want to find acceleration, so all we need is to use this equation here. We know F, we know M1, we know M2. Okay, so the solution that we are looking for is going to be A equal to F divided by M1 plus M2. So that's the solution. Okay, I didn't ask for the normal, so you don't have to solve, we don't have to worry about that, right? I asked it only for the acceleration. So at the end, we didn't use the second equation here because I didn't ask for the normal. Okay. Now we can, that's the easiest of the three problems, okay? In this problem, note that in this problem, we did not use Newton's third law of motion, but only the second law. Okay. 243, let's see. Yeah, let's go a little bit more, right? Now we are going to do item number 2. In item number 2, we want to find out what is the value of the force that 2 applies to 1. Okay, that's what we want to do. Here you go. Go back here, go back here, go back here. The force that mass 2 applies on mass 1, using mass 1 alone as the system. Okay, I already did the free body diagram. And according to this free body diagram, we are going to have two equations, one along the x direction, the other along the y direction. Right? Just math 1 treated as my system. Okay, and now I am using Newton's third law of motion. I'm using Newton's third law of motion because this mass 1 is applying a force to mass 2. And because those two masses are interacting with each other, 2 must apply a force equal in magnitude in opposite direction on mass number 1. Okay, that's how I got this mass number 1 here, right? Going back to the drawing here. Here you go. So here you go. Free body diagram applied just to mass number 1. Here you go. Because mass number 1 is contacting mass number 2, mass number 1 is applying a force on 2, F sub 1, 2. Consequently, because those two masses are interacting with each other, it means that mass number 2 also exerts a force on mass number 1, which is force of 2 in 1. But because we're considering M1 as being our system, we don't need to worry about this other force here, right? That's the whole idea. And now we can go ahead and by the way, we already solved the acceleration of the problem, right? We already know the acceleration of this set from the previous problem. The two masses move in tandem. Consequently, the acceleration of 1 is going to be equal to the acceleration of 2. And let's go ahead and get our Newton's second law of motion. Okay, net force applied to my system is going to be just mass 1 times acceleration. Okay? But the net force applied to mass number 1 can also be written down in terms of the external force F minus this counter force F21. And by the way, I'm assuming that this value here is positive, okay? That's why I put this negative here in front of. We can get the second equation, but we don't need the second equation. The second equation would be N1 equal to M1G. That's what the second equation would be along the y direction. We also have a second equation along the y-axis, but we don't need to use it because it does not affect the value of F21. Okay? We want to find F21. And since the norm and the weight do not affect it, right? We don't have to worry about it. And now, remember, we want to find F of 2 applied to 1. We do not need the net force anymore. And now we can use the solution of our previous problem to substitute right in here for A. And that's going to be, if you remember, okay, here you go, F divided by, let's see, yeah, M1 plus M2. Remember that? That was the result that we got. F divided by M1 plus M2. That's what I did, I substitute right here. And now, we know this guy, we know this guy, we know this guy, we know this guy. We know everything but this one here. Consequently, we can solve our problem, right? Here you go. That's how it looks like. Step by step. Multiply everything by -1. That's what I'm going to do right now. -1 here. -1 is plus. -1 right in here. And then we solve for F21. Okay. When F goes to the other side, the negative sign change to positive sign, and we get that. Let's see if we can do better than that. We can come up with a simpler result by putting everything under the same denominator. Okay, and that's what I'm going to do now. Here you go. Putting everything under the same denominator. When we do that, we also introduce this multiplicative term here, M1 plus M2, right? M1 plus M2 canceling out with those two, so we end up with just this F, right? But why am I doing that? Because, well, I'm doing that because we will be able to come up with a simpler result. Now I keep them all, here you go, under the same denominator, right? And look what we have, this minus M1F cancel with this plus M1F, okay? Providing us with a simpler result. That's why I put, okay, F1 is equal to that. Or I can even write it in a different way. I'm going to write it in a different way like that. The ratio here that has no units, kilogram cancel out with kilogram, right? No unit, unitless ratio. And a term that has a unit of Newton. And let's see, that's what the value of the force of one applied. And by the way, let's not forget that force of two applied to one. And now I'm going to use Newton's third law of motion, right? Newton's third law of motion states that, okay? States that F of 2 applied to 1 is equal to minus of F of 1 applied to 2. There's a little inconsistent with the notation, okay? Inconsistency in the notation. But I'll let you figure out on your own. Now let's do item number 3. Now in item number 3, what I'm asking you to do in item number 3. Verify the acceleration following the first item by using mass 2 alone as your system and apply. Okay, so what I mean exactly here, find the acceleration using the result in item 2 and by using mass 2 alone as your system. Okay, that's what I mean. There's a better way. Okay. Now suppose that you didn't have calculated the acceleration here, right? So basically, I'm asking you to find the acceleration using this result and using the last free body diagram. That's what I mean. Okay? Suppose you didn't know how to solve this problem here, or you didn't solve this problem here. Basically, you know, this last item, what's this last item? This last item, you are gonna find the acceleration, by using, let's see here. I'm gonna illustrate it. Item number 3. Item number 3. Item number 3. Find the acceleration using the free body diagram of item 2 and the free body diagram that considers M2 as the system. That's what it is. Okay, and I'm going to emphasize it. I'm going to emphasize it here. Find the acceleration using those 2 free body diagrams. That's what I'm asking. Okay, you get the idea? Okay, I'm gonna even put them in a table. I'm repeating it, okay, for item 3. That's for item I. No. One more student coming. Here you go. It's this one that I want. I placed it in the wrong place. Edit. Okay. And then I'm gonna put it in a single, those 2 drawings. Okay. Insert table, 1, 2. Good. That's the free body diagram of item 2. And that's the free body diagram of item 3. Here you go. Free body diagram of item II. Free body diagram of item III. Like that. That's what I'm asking, right? Basically, I'm asking to find the acceleration. I'm gonna put this in here. Here you go. It is possible. Okay, so only mass 1 treated as their system. Only mass 2 treated as your system. Okay, so we have another student joining us now, right? Who joined us? Let's see. Yeah, there's. Well, let's take a break for now. Okay, and then we can solve this problem. Let's say it is 10:58. Break. Any questions about that so far? Okay. No break. 10:59 a.m. to 11:14 a.m. And then after the break, we solve that. Okay, so I see you in 15 minutes. Okay. Stop sharing. I am back now. And let's share here the screen right here. Okay. So remember that I told you each of those drawings, each of those free body diagrams, they are used to create one or more equations, right? Here you go. Here's one free body diagram. Here is one vectorial equation. Here is another different free body diagram. Here is another different equation. Okay? And then we have our third free body diagram. And this third free body diagram is going to generate another equation. Okay, so let's get this other final equation here in place. Here you go. It's gonna be like that. Here you go. Our final equation from our third free body diagram. Let's see, this one should be here, right here. Should look like the following. Now, in our third free body diagram, we have only this force here propelling the mass, right? In the previous one, we had this force propelling the mass, and we had a counter force countering the external force. But now we are going to have just the so-called reaction force, right? F12, propelling our mass number 2. Okay? And now what we want to do? We want to use those two free body diagrams to find the acceleration. Okay? That's what we want to do. Okay, so here you go. Basically, it's like that, assuming that we should have reformulate the problem in a different way, okay? Assuming that you don't know F12 and A, right? Find these two values using the two free body diagrams, the above, using the above two free body diagrams, okay? That's the problem that we want to solve. That is the problem that we want to solve. Here you go, okay? In order to solve this problem, we must use the equations associated with the two free body diagrams, okay? One of them is this one, and then we gotta use the other one too. Let's see if it's two here. Yeah, we have to use the other one as well. Like that, okay? And I'm going to emphasize we are solving this problem as though as we do not know A nor F21, okay? Or F12. And by the way, what we have here is supposed to be a magnitude, okay? Here too is supposed to be a magnitude. I'm gonna leave this way. It's supposed to be a magnitude. And by the way, now I'm going to use another equation, right, that you already know. That comes from Newton's third law of motion. Okay, they relate to each other, right? Here you go, unknowns. What are the unknowns? A is an unknown. F12 is a second unknown. And F21 is a second unknown. 3 unknowns for 3 equations. Okay? Now, wait a minute. There's something wrong here. The way to do it, yeah, the way to do it would be like that. Magnitude of F12 is equal to magnitude of F21, okay? That's the right way of doing it. Yeah. Okay? That's the right way of doing it. Let me emphasize here the A. So now, okay, we will be able to replace what I have here in here, okay? And now I don't need this equation anymore. I already used it. Now I have 2 equations for 2 unknowns. Huh? And look here. Look here. I can place this guy right in here, right? Here you go. Okay, so I'm gonna copy that and place it right in here. And I don't need this third equation anymore. Now, you know, my mass is always positive. Consequently, I can take it out from the magnitude. The acceleration is from the left to the right, which is the positive x direction. So I can say the magnitude of A is going to be equal to A itself. And now I can solve my problem, right? Here you go. Equal M2A plus M1A. Okay. M2 plus M1. Like that. And we get exactly the same solution that we had before. Different way of solving the same problem, right? M1 plus M2. Here you go. Like that. Let me erase that. Note C, and I'm going to emphasize note C that each of these figures, note C that each of these figures can be used to determine a vectorial equation that can be used to solve our problems. That's the little secret of the free body diagram. Each free body diagram can be used to generate one equation, one or more equations. To generate one, let's put here one vectorial equation. Let's put it this way. That's better. And then we don't have to worry about all this thing once we have a vectorial equation, right? Depending on the type of problem, you're going to have 1, 2, or 3 scalar equations. That's a very nice problem that if you understand it well, you will be able to solve almost any problem in physics involving forces and the third law of physics. Now, let me just a reminder, right? Reminder, lab report 1 is due Wednesday. Okay, don't forget just the spreadsheet. It's due Wednesday, the day after tomorrow. Don't forget just the spreadsheet. And now we can go back to see what was the topics we covered so far in chapter 4. Right? Okay, Newton's third law. We're done with Newton's third law. Like I said, we cover half of this chapter. We're going to cover the other half later on. And we cover everything but the other half of this chapter here, okay? So we're going to go back to the gravitational force later on. Before we do that, we have to start covering chapter 5. And let's take a look at the book as well. Okay. Wow, it's taking time. You know what? Let us finish chapter 4. And then we are going to go back to it again once we start circular motion. And then why this guy here is not, let me see what's going on here. Well, maybe that must be the AWS incident, right? Okay, that's, we don't need. I'm not gonna, let's finish this chapter here. We can finish this chapter now. And then we are gonna go back to this chapter once we do uniform circular motion, okay? Which is chapter 5. Okay, so here you go. Laws of motion. Laws of motion. Newton's first law of motion. Right? Okay, just to remind you, if an object at rest or moving with constant velocity, then the net force applied to this object is 0. And the converse is also true. The converse is also true. We go. The converse is also true. I.e., if the net force applied to an object is 0, the object may be either at rest or moving with constant velocity. Newton's second law of motion. It's hard to emphasize how important laws are in physics, okay? That is stuff that gives you the Nobel Prize. If you manage to discover a new law of physics, that's the stuff that makes you a candidate for a Nobel Prize in physics. Okay? Third law of motion. And there is one more law. There is one more Newton's law. Here you go. There is the law of universal gravitation. Another law attributed to Newton, another law attributed to Newton is the law of universal gravitation. Universal gravitation. Okay. Okay, what you have to know, and I mentioned that before, everything that has a mass produces a gravitational force. Everything. Okay. And there is an equation. And there is an equation that relates this force with the mass of the objects and their distance. Okay. Everything that has mass produces a gravitational force. Okay. However, keep in mind, okay, that this force is very small, almost imperceptible. For objects that have small masses. And by small, I mean, by small mass, I mean masses that are less than that of a planetary object. Okay. There's an equation, by the way, there's an equation that relates this force with the mass of the object. One of the equations you already know. Now, one of those equations you already know. One of them is that the gravitational force that the Earth apply to an object of mass m is mg. But there is another equation that's far more generic than this one that you see right here. However, there is another equation that is far more generic and powerful too, right? Than the above equation, than the above one. This equation is, you go, the weight or the gravitational force applied to, let's say, to a mass. Let's see here. Let's use yeah, the gravitational force. Here you go. The gravitational force between two masses is given by this equation. Okay, it's given by this equation. And even better, I'm gonna I'm gonna put the different format. I'm gonna put mass lowercase m, okay, to make it more intuitive. Uppercase m. So let's say we have two masses. One smaller mass m and a larger mass big M. Okay. The force between those two masses is going to be given by this equation that you see. And by the way, we can reorganize this thing here. It's going to be like that, M, like that. And I'm going to go even further. I'm going to put a big G here upstairs. Okay. And this D here is the distance between them. Notice that this M stands for this other M here. And this acceleration of gravity is exactly this term that you see right here. Okay? So let's take a look at the drawing. Let's see if I have my drawing here. No, I gotta get another one. I'm going to illustrate that for you. What a shame I don't have it. Yeah. Let's see here. Impossible, I don't have it. Work. Let's see this one here. Huh. Work linear motion, rotational motion. I'm disappointed. Maybe it's here. This topic is something that I usually cover in a different order. So it must be somewhere. Let's see here. Somewhere here in my slide. Okay, let's see. Okay. Huh. Interesting. I didn't. Okay, that's what I want. Let me put that in a separate one. I am surprised. Great. What's that? New blank presentation. Okay. Let's see. Back up. Let's see. Colleges. Harbor. 2005. Illustrations. Okay, good. Newton's law of motion. 05. Gravitational force. Universal gravitation. like that. Okay, now here you go. Let's start. Universal gravitation. Okay, consider a mass, a small mass. I'm going to put it lowercase m instead of uppercase m1. Let's put lowercase m. Okay, and then if we put another mass next to it, can be larger, can be smaller, doesn't matter, which I'm going to call capital M, you know, and those two masses are separated by a distance b. Okay, what happens? Something is going to happen. Okay, there will be a force applied to this mass. And then I'm going to even change the notation. Instead of 1 and 2, I'm going to put capital force, the capital M applied to lowercase m. Better, right? Similarly, likewise, because those two objects are interacting with one another, there will be also another force in the system, which is the force that lowercase m applies to uppercase m. Got the idea? Okay. And this force, right, is a gravitational force given by that equation that I showed to you. Okay, let me erase it. Oh, one more thing. Let's see here. One more thing. Okay. This D can be here written instead of D, right? We can come up and call it distance between instead of D, now I'm gonna call it distance from mass lower m to upper m, okay? I'm gonna play the movie again very soon. And on the top of that, we also have this unit vector that is in the same direction as this vector here, right? But it's shorter because it has a unit vector. And this force, okay, is given by that equation that you saw. Can you remember that? Lower m, g big M d square divided by d square, okay? And instead of f big of sub g, now let's write that down as being, you know, FMM. Okay. This, okay. This you know what it is. This you know what it is. This you know what it is. What about this one here, right? This one here is a constant, a very important constant that can be measured in the laboratory. Okay, it's not the lowercase g, it's the uppercase g. The lowercase g stands for acceleration of gravity, which is 10 meters per second squared nearby the surface of the Earth. But this big G, right, is the gravitational constant that's good everywhere in the universe, and it has a numeric value with units that's different from the acceleration of gravity, and is given by this value that you see here. Okay, that's the unit of my gravitational constant. Note C that big G and G are completely different parameters. Okay, let's do that. G, lowercase g, and big G are completely different parameters. The first one is the acceleration of gravity, and has unit of acceleration, meter per second square, right? The second one of units acceleration. The second one is a universal constant that has its own unit, and that is different. That is different from the previous unit. Okay? Don't mix up big G with lowercase g, right? One is for acceleration and the other is for something else. It's a parameter that goes into our law of universal gravitation. Okay? The unit that we have here is completely different from the unit that we have here. You can even, let's take a look. What unit is this one? What the ultimate unit of this big G, right? Ultimate unit in terms of the meter, kilograms, and seconds, right? Here you go. The Newton is like I said, it's kilogram, meter per second square, like that, right? Kilogram meters per second square. That's what the Newton is. I'm gonna put it all separately. Here you go, like that. Yeah, better. All right, let's see. Kilogram cancels out this kilogram, right? Kilogram cancels out with this kilogram. This meter combined with the other one. And look at the strange unit that we get, right? It's meter cube per second square kilogram. Is a unit that's completely different from the unit of acceleration. Okay? And now what we have to do. Let me erase that. Oops. Okay. Let's come up with some examples. Simple example. Consider a man mass 80 kilograms on the surface of the Earth. Of his weight using the equation mg, right? And the universal law of gravitation. What you have to know, the mass of the Earth is given by the mass of the mass and diameter of the Earth are given by, we can look at the internet, mass and diameter and radius, right, of Earth. Here you go. Mass is it's approximately 6, okay? 10 times to the 24 kilograms. And the radius is given by, here's 10 to the 24, the power. And here's 10 to the 6. Okay? Simple example. And then we can use, let's see, meter. Here we go. Solution. You already know that by using, the first one, mg, right? You get weight equal to mg equal to 80 kilograms times 10 meters per second square. We get 800 kilograms meter per second square. Meter per second square, which is equal to 800 newtons. Simple enough, right? What about number 2? Number 2 is more complicated. Number 2, we have to use this equation right in here. The weight. Universal law of gravitation. Universal law of gravitation. Here you go. Like that, right? And then we can use Excel to come up with this. Or you can use your calculator too. I prefer to use Excel. Right in here. Fall 25, that's good. Let's see here. Okay, so I'm gonna write that down, big G. And then we have the units. Lowercase g is kilograms. Uppercase m, kilograms as well. What else do we need? The distance, right? Distance, which in this case is the radius of the Earth. Okay, and then what we end up having here is going to be the weight of the person. Let's see if I have a illustration. Yeah, I will have to come up with an illustration on my, right in here. Okay, right in here. Here is the Earth, and here's the individual, okay, sitting over the surface of the Earth. The distance of the individual to the center of the Earth is the radius of the Earth, okay? And I'm going to, what else? I'm going to put here, this is big M. This is lowercase m. Oh, lowercase m, okay? And let's not forget what you have right in here is the radius of the Earth. Is the radius of the Earth. That's what this problem is all about. Now let's going back to our radius of the Earth. And now we're going to have, what's that? Yeah, that would be my equation. My equation would be big G times lower m times mass of the Earth divided by the radius of the Earth square. Okay, of course, I'm not going to get the value, but here I'm going to put 80. Here I'm going to put what? 6 times 10 to 24, right? 596, right? Let's take a look at the internet again. What's the value of the mass of the Earth? It's almost 6, 597, 10 to 24. Okay, so let's put 597 here. 597, 10 to 24 kilograms. The radius is 637 million meters, 10 to the 6. 637 6.37 million meters. And we need this value here that has that fancy unit, right? And the fancy unit is Newton meter square over kilogram square. Newton meter square over kilogram square. Superscript. And we have, oh, didn't do it. Superscript. Yeah, here you go. And now what value that's going to be? I don't memorize those values, so you're not required to memorize either. Of course, it always helps, right? Helps you solve a problem more quickly. And 6 e times 10 to minus 11, 6.674. 6.674 e to minus 11. Okay, and now look what we get. It's already calculated automatically for me, right? I got 785, which is very close, to the other one. The other one was 800, right? We can even calculate what's going to be the percentage difference between them. The percentage difference between them is going to be what? ABS, this minus this, times 100 divided by this one here. Is 1% difference only. 1% difference. We got 800, we got 800 because we used 10 meters per second square. But what if you were to use, not 10 meters per second square, what if you were to use 9.8 meters per second square, right? It's going to be even closer. Here you go. See that? 0.2% only. 0.2% difference only. 784 compared to 785. And I believe it would be 9.82. Let me see. Yeah, 9.82. Like that. Even smaller. Okay. So that's one simple application of Newton's universal law of gravitation. Okay, and we're going to have our break again now. And when we return, we'll do another example just to compare the gravitational force between small masses, okay? And break is going to be 11, right? Let's see here. No, it's 12. 12 p.m. Well, 15 p.m., right? Any questions before the break? Okay, so see you shortly. Okay, I'm back here. Okay, so here you go. For this case, we are getting exactly 785, right? 85, 786. Okay, let's round it up. 786 newtons. Okay, the above result is only how much percent difference? It's only 2% different. It's only 2% different from the simpler model of W equal to mg for g equal to 10 meters per second squared. Okay. Just keep in mind that the result for the universal law of gravitation is more generic than the one for mg. Okay, keep that in mind. It's a more generic theory than the one for mg. Now let's do another example. You know, another example. Individuals of 80 kilograms each are 1 meter apart from each other. Calculate the gravitational force between them. Okay. So now is another example, so you can have an idea of the orders of magnitude that we're talking about when we are dealing with planetary masses and regular masses from small objects. Okay, so the situation, let's see here. The situation is the following. Okay, we have one guy here and another guy, they're both sitting at the surface of the Earth, right? Here you go. Separate by 1 meter of distance. Here you go. I'm gonna put it here on the side, and then I'm going to do another drawing. Okay, so let me get, let's put like that, one here and the other one here, and they are separated by a distance of 1 meter. Here you go. That's the one I want. One more student coming. Who is that? Armand. Good. Here you go. So Armand has joined us, right, Armand? Here you go. That's the distance, D. In this case, it's 1 meter. Let's see. Okay, good. Did you have any problems logging in, Ivan, or which was straightforward? You had? Ah. So what was the problem? The link was not working, or? Okay, so pretty very strange, huh? It's interesting. Okay. And yeah, canvas is down. That's right. But I suspect canvas is down, and because canvas is down, also the zoom of LACCD is down as well. But remember, I'm using my own personal private Zoom account. So I presume that the AWS incident didn't affect the private Zoom accounts. I presume, okay? But you're telling me that you're having problems, right, with the link? But let's go back here to the problem. Okay, so here we go. 225 is the same equation, different masses, right? Solution. Same equation, different masses. Here we go. 80 kilograms, right? And big G is how much? That 6 point whatever, 6.67 times 10 to minus 11. I'm going to put all the units there. Right in here. The mass of the other guy is 80 kilograms. So we substitute right in here. And the distance between them is 1 meter. Like that. Okay? And then we put there in we put here in Excel. Okay? Now, all I have to do, in the previous problem, right, I put the mass of the Earth. But all I have to do now is to replace this value here by 80 kilograms. And let's see. Oh, yeah, I also have to replace the radius here by 1. Yeah. 80 kilograms, 80 kilograms. Okay, now, and then what are we getting? We don't, this one you don't disconsider, okay? You know what? Let me see. Let me do it differently. I don't want to lose that. Okay, it's 80 kilograms. 80 kilograms. The distance between them is going to be 1 meter. Here, it's not applicable, okay? No, wait a minute. That's applicable. Yeah, this is the one we want. And look at the value. Here is not applicable because this one is empty, okay? Look at the value that I'm getting. It's a very small value compared to this one. I'm going to write that down, right? 4.3 times 10 to minus 7 newtons. 4.3 times 10 to minus 7 newtons, okay? The gravitational force that one individual exerts in the other individual exerts on the other is much smaller than the gravitational force that the Earth exerts in each one. For this reason, this force can be neglected, okay? It doesn't, we don't have to worry about this force in our day-to-day life because it's too small. You know, the previous force, the force of attraction of the Earth is 800 newtons, close to 800 newtons. It's like 9 orders of magnitude greater than this force here. So in our daily life, we can neglect any force of attraction that we feel, right? When walking around the block and so on, okay? One more thing, right? One more thing. Remember that I told you, here you go. I told you that this, what you see right in here, what you see right in here is also equal to what you see right in here, right? If you equal those two equations, what do we get? You get that the acceleration of gravity depends on the distance between, on the distance from the center of the Earth, okay? From the center of the Earth. Okay, so here you go. Going back to the equation of the weight, to the weight equation, going back to the weight equation, okay? Here you go. Note, see that the G depends on the mass of the Earth or the any other planet and the distance of the object from the center of the Earth. Okay, this G depends on that, on those two parameters. So here you go. So the higher we go, so the above equation states that the further we go from the center of the Earth, comma, the lower the acceleration of gravity, okay? The lower the acceleration of gravity. And we can come up with a nice simulation in Excel as well. I always do that with my students, okay? Every year that I teach this course, I do that. Oh, here you go. I can come up with the acceleration of gravity in terms, superscript, of the distance to the planet, in terms of the distance from the center of the planet. Here you go, in meters, right? We start with the radius of the planet, sitting at the surface of the planet. And then as we climb, here you go, this is, let's put here R. R, the radius of the planet. And then we are going to have the height as well. Here you go, height in meters. And the equation is going to be given by that equation that you saw, big G times mass of the Earth divided by, you know, the distance of the object from the center of the Earth. So that distance would be the radius of the Earth plus the height of the object with respect to the mean sea level. Let's see what's going on here. Mass of the Earth. I'm getting a funny result. Why I'm getting that? Oh, that's because I forgot to raise to the second power, right? Here you go. That's why. Now I should get the right one. Yeah, here you go. And I'm gonna put in the proper format, in an easier format, numeric format, number two, not general, I want number. Here you go. At the surface of Earth, we get exactly 9.82 meters per second square with that equation, okay? But as we climb higher and higher, let me put here a different format again, number, yeah? As we climb higher and higher, let's start with 10,000 meters. The Earth doesn't change, okay? What's going on here? No, something wrong here. Oh, yes, that's right. Okay, so I'm gonna do the following. I'm going to put a dollar sign here. I'm gonna put another dollar sign here. Yeah, and now there's no problem. And as we climb higher and higher, right? Let me put a format cell number. I don't want the decimal places whatsoever. Here you go, better. 10,000 meters and so on, right? The radius of the Earth doesn't change. What did I do here? Let me show you exactly what I did here. What we are doing here is the following. What we are doing here is the following. We're rising the mass, right? That's the height of my mass, okay? And that's the height h. And the height h format shape. This one here, good. That's gonna be h. This one is m. And this other one here is h. Like that, okay? And I'm gonna put a dash. Like that. Like that, okay? That's what I'm doing. The higher we go, what happens to the acceleration of gravity? It decreases, right? The higher we go. And let's not forget what I did here. I have to sum the radius of the Earth with the height that the object is located, right? So going back to my equation, right in here, this distance that you see right in here is in reality the radius of the Earth plus the height of the object. And as he climbs further and further away, oops. Okay. The acceleration of gravity decreases. 60,000 meters is 60 kilometers. Next is going to be 70,000 meters, 80. 70,000 is 70 kilometers, 80, 90, 100. 100 kilometers is considered the line of Kármán, Kármán's line, which is considered the point where the space starts. At the point where the space starts, the acceleration of gravity is still 9.5 meters per second square. Okay? It's not much different from the acceleration at the surface. And now if you keep on climbing, okay? Now let's say instead of increasing every every 10,000 meters. Let's increase every 100,000 meters or 100 kilometers, right? You should go lower fast. See, 600 kilometers. This is the distance. Here's the altitude of the space station between 400 and 600 kilometers. The altitude of space station. Okay, as we move further and further away, the acceleration of gravity should decrease. Okay, and so on. Here is 2,600 kilometers. Okay, here is already 20,000 kilometers. 20,000 kilometers is half the distance between the Earth and the altitude of the synchronous satellites, the telecommunication satellites. The telecommunication satellites sit at a distance of, at an orbit of 40,000 kilometers, okay? And note, see that at this height, then the acceleration of gravity decreases significantly, okay? Let's plot it. We can plot and see how, here you go. That's how the acceleration of gravity changes as you increase the height. At near Earth orbit, around here, this region, is very close to 9 meters per second square. But as we move further and further away, 20 million meters or 20,000 kilometers, you get acceleration of gravity that's on the order of half meter per second square. Okay? So that's how we got that value of 10 meters per second square, by cranking up this equation that you saw right in here. 439 now. Any questions about that? So let's see if we have anything else. Okay. Let me see if we can finally get Wiley Plus here. I want to access the book online. Let's see if it works now. I'm suspecting that that AWS incident is affecting Wiley as well. Oh man, yeah, it's not going right. But it's not affecting the other services. It's not affecting AOL. It's not affecting WhatsApp, huh? We did apparent wait. So now we can state that we close this chapter. Yeah, unfortunately, I cannot get into the book, but okay, so everything is covered in this chapter 4. And now we can start thinking in terms of the chapter 5, okay? And chapter 5 is going to be uniform circular motion. Let's take a look here at the sections of uniform circular motion. We have only 10 minutes left, right? 9 minutes, that's not going to be possible to do much on that. So let me just display to you what is going to come in chapter 5. Right in here. Chapter 5. Okay. Chapter 5, uniform circular motion, centripetal acceleration, centripetal force, banked curves, interesting circular and satellites in circular orbits. That we are going to use the universal law of gravity. Okay. Apparent weightlessness. Okay. And artificial gravity. Apparent weightless, we already did it, which is the apparent weight. And then we're going to look at a different approach, okay? Instead of having the elevator, what you're going to do here, we did the problems on apparent weight. Yeah, we did that, but it was in the one-dimensional weightless or apparent weight, okay? Here in this problem, in this chapter, we are going to look at two-dimensional weightlessness, or two-dimensional apparent weight. And then we're going to look at vertical circular motion as well. That's what's planned for chapter 5. Just going back to our schedules here, right? So here you go. Here is going to be chapter 5. We're going to have, next time we meet, I will start uniform circular motion, and then we are going to do lab number 2. That should be chapter 5. Okay. UCM lab 2. Okay, lab 2 is going to be let's see what's going to be lab 2. Lab 2 must be accelerated motion. Let's make sure it is accelerated motion. Labs. Raw data. Yeah, that's right. That's accelerated motion. Lab 2, accelerated motion. So UAM, right? Uniform accelerated motion. Yeah, let's put it this way, accelerated motion. Yeah. Uniformly. Okay, better now. Yeah. Uniform circular motion is going to be, you are going to lecture on uniform circular motion. Let's not forget that the lab number 1 is due next time. And because we are doing uniformly accelerated motion, it should be topic of chapter 2, right? Topic of chapter 2 is going to be the lecture on chapter 5. And very soon we are going to have to adjust our clocks, right? Very soon it's going to be the other weekend, not this weekend, the other. And let's not forget, we are going to have an exam on November 20th. No, it's not November 20th, sorry, November 12th. November 12th is going to be a little bit less than 1 month. So 1, 2, 3 weeks and a half. 3 weeks and 2 days. In 3 weeks and 2 days, we're going to have our second exam, okay? Any questions about that? So we can stop here now. And today is Monday. We have my office hours right now. If you want to stay around and talk a little bit about my material, I'll be available, okay? So thank you for attending the class today, and I'll see you on Wednesday.
Thank you, Professor.
Welcome.
Hello, Professor.
Yeah, who is that?
This is Armand.
Oh, yeah, hi.
Hi. I have a question because so the lab, I just have one. I just want to know I'm doing it right
Uh-huh.
for the lab one. Is that
You have
okay or
what?
no? The lab one, I just want to know if I did it right.
Uh-huh. Okay.
Can you see can I share my screen and you tell me if I did it
Sure.
right or wrong?
Okay, you want to share the screen? Go ahead.
One second.
Dez por dia? Nossa Senhora. Como é que é possível isso?
Okay, I'm sharing it.
Yeah, what's the question?
I just want to know if I'm doing it right. And the thing is for the CL min max, like I don't know if it's just because I had the issue before, remember?
Oh,
With my because I'm on the MacBook and I don't know why, but like I had to do it a different way. So it's kind of hard to find the CL min max because I can't find the data.
no, you already have everything that you need. You need to, there is a table on Canvas that
Mm-hmm.
that I provide to you at the very beginning of the course. Okay,
Mm-hmm.
we have the table there in your hard drive.
Okay. Okay. And then I just want to know if this is correct. Like these inputs.
Let's see. Yeah, looks like everything was okay. Let's see, micrometer 96. Yeah, you put the correct n, you put the correct m, which is the equation r squared is correct. And now to find the CL min and max, you have to use that table that I distributed to
Okay.
you all.
Okay.
Okay,
Okay.
and huh?
And then for this, I have to input something here, or do I just leave
Yeah,
these what it
yeah,
is?
yeah. The slope of each graph you have to input there. The slope for the ruler, the slope for the vernier caliper, the slope for the micrometer. Okay, you got
Is
it.
it one of these? Is it one of these numbers?
Yeah,
Or
it's
I
one
have to
of this.
find,
Which one is the ruler? Which one is the
isn't
ruler?
it the ruler is this one? So it should be 0.9798.
No, that's the r squared. That's not the slope. The slope
Oh,
is the okay. The slope you go to the equation. See that the
that's the
equation there.
equation. So I just okay, I understand. So what do I do for this? Do I input the equation?
No. You input only the slope. What's the slope in the equation?
Is it the
Yeah,
8118? Okay.
A118. So
Is
you
it the
type
point
it.
four as well? Do I put the point four to X?
Yeah,
No, or just
yeah,
yeah?
yeah. You can
So
put it.
eight, so the correct, so like for example, this one would be 8118
Yeah.
4X.
No. Just the number. There's just the number. X is not the slope, right?
So
It's
just
just
this,
what
correct?
goes. Yeah, just the number.
And then the units is correct, right? The kilogram.
Oh, the unit is going to be the unit of mass divided by the unit of volume. Yeah, that's right.
Okay.
Yeah.
All right. Okay, yeah, that's
Now,
all I
now,
want
now,
to
do
know.
you see the percentage difference down there now? It's 3%. See that?
Oh, okay, I see.
Okay.
See, but the thing is, it says 3.8, so I guess that's 3%.
Yeah. This is 3%. You gotta change the format. Change the format so it can display in numeric
How
format.
do I do that? How do I do that?
Go ahead. Highlight those cells.
Okay.
Highlight.
Like this?
No, you gotta return, apply return. You just now undo everything, undo
Yeah.
everything,
Am I doing it?
undo. Yeah, you gotta
It's
be
not
careful
working.
when you
It's
do
not
that.
working.
It's not
It's not
working.
working. Hold on. How do I
Wow.
do this? Oh, here, I did it.
Did you manage? Okay, good. Now highlight it.
Like this?
Click and drag,
Now
right?
what?
Now
Yeah.
right click. Oh, no, highlight again. Click and drag.
You want me to do both of these or just this one?
Yeah, do everything in all the six cells, all the six
Okay.
cells. Okay. Yeah, here you go. Click and good. Right click.
Sorry.
Oh, it unhighlighted.
Yeah.
Strange. Try it again. Right click. What?
It's not letting me because I don't have
What?
right clicks. I'm on the MacBook. Okay, I
That's
got it.
okay. Now
All right,
you
I
did.
got it.
Okay, don't delete. Don't delete.
Yeah.
Format cells. Format cells.
Okay.
Yeah. Format cells. Okay. Now let's see number. Go in the tab number. Yeah, good. Now instead of scientific, put number, the second one. Okay. And I'll put two decimal places there. instead of 0 decimal places, put 2, okay? Okay, good. Now do you see that?
Okay. I
Now
see it.
you can see the numbers more easily. And then you gotta do for the vernier caliper and the micrometer, okay?
Perfect. Okay. Yeah,
The
that's
vernier
okay.
caliper.
And then do I put the same, do I put the input number the same thing I do for these or just leave these the same?
Oh yeah, you have to work on the, okay, what's missing there is the units are missing. You didn't put the units, okay? And you
For
have
M3.
also, and you also have to work on the significant digits. You didn't put the number in the proper format, okay? Right
Do I
now,
have to change these? Do I have to change these to the same thing that I just changed with the other numbers or no?
yeah, you have to change, but you have to know how many decimal places to put there, okay? You have to
Okay.
know, you have to know how
So
many
I guess
decimal places to put.
three. So I guess three.
Uh,
No,
I
actually no, five.
undo. Yeah, good. You gotta be careful, okay? When you click the
Yeah.
cell, you can you can erase the formula that's in there.
So do I change these to 5 decimal places?
Well, it depends. It depends for the ruler, okay?
So this
For
would
the
be
ruler,
two.
highlight the numbers. Why is not highlighting? Okay, now you highlighted.
So I
Yeah.
guess these would be two, correct?
Let's see. Format cell. You see meter. Actually, it has to be 3 decimal places. 3 decimal places because it's in millimeter. The resolution of the ruler is in millimeter. Okay.
Yeah, yeah, yeah.
Okay. Now the vernier caliper. What's the resolution of the vernier caliper?
That'd be four.
Yeah, that's right. 4 decimal places, right? 4 decimal places, not 4 significant digits.
Yeah, I know. 4 decimal places.
Four. What about the micrometer?
That'd be five.
5. Yeah. Format
And then
cells.
for the density, that would be five. Or what would I do for the density for like the top for the steel?
One minute. Let's finish this
Yeah,
one
let's do
first.
one at a time.
Yeah,
Yeah, I guess.
let's finish this one first. Good. Okay. Now for the density. No, for the void. Oh, you gotta be careful. Undo. Yeah, here you go. Now,
So
okay. Do for the mass now. Do for the math now. Let's leave the volume for later on.
that should be four, correct?
Let's see. You gotta look at the notes. Okay, it's not 4. It is 5. For the mass is
Five.
5 decimal places
Okay.
because it's 100ths of a gram. Okay.
Okay.
Now you have to worry about the volume. Okay.
Okay.
You have to worry. You
So
gotta look at the rules for the volume for the multiplication.
would it be five as well?
Well, here you go. The number
Or if it's
of
division, if it's division, would it be the same?
what did you say?
If it's division or multiplication,
No, it's
would it be?
multiplication.
Oh, it would be three, right? It would be three for this.
Well, wait a minute. Wait a minute. Let's go slow. What's the
Hmm.
rule for multiplication?
Isn't it the lowest amount of significant figures?
The lowest amount of what?
Significant figures?
Yeah. Okay. Good. How
So it'd
many
be
six?
three.
Wait a minute. Let's go slowly. How many significant figures do you have for this first value here of the ruler?
Three.
No, it's not 3. 3 is the
Wait.
decimal places. Okay, you have
Oh, my bad.
3.
So four. So four.
No,
Oh,
it's not 4. Yeah,
two,
it's
two,
2.
two,
That's right.
two, two,
It's
two. Yeah, yeah,
non-zero
yeah.
numbers, right?
Sorry, yeah, yeah.
So
Sorry, yeah.
if you have 2 on for the diameter, you must have
So it'd
2
be
for the
two.
volume as well.
Yeah, so it'd be two.
Okay.
So it'd be two for all these, correct?
Yeah. Uh-huh. So this one you can either right click, format cell, number. But don't forget, it's 2 significant digits. It's not 2 decimal places.
Yeah. So I
Okay.
need to do. So it'd have to be. So what would that be for?
Oh, well, let's see. Let's see.
Nope.
No, not yet. There is a better way of doing that. Okay, instead of putting numeric format, you can
What do I
leave
do?
it in the scientific format. Okay,
Okay.
leave it in the scientific format, and now just add one decimal place there. Just add one decimal place there, and now click OK. Now look what you got. Now you got two significant digits, right?
Yeah.
Okay. Because this number is very small, it'll take you forever to figure out how many.
Just leave it like this then, I guess.
Yeah,
So for this, I would do three significant figures.
three significant figures. Three significant figures is going to be two decimal places for this one.
I understand. Okay, and this would be three.
And
That's three. Okay, I understand. Okay, so then this one would be,
this one
I
you don't
guess,
have to worry. This one you don't have to
just
worry
leave
because
it.
it's a theoretical number. It's not a measurement.
Can you help me with just so I can't find the CL min max
Well,
what is
well,
it called?
first you need the table. Do you have the table there in your computer?
Oh, I can't open it right now, but
Yeah, but
um
you cannot open because why is that? Because you cannot access Canvas.
yeah, I know.
Yeah,
Yeah.
okay,
Okay.
okay. So make sure something like that doesn't happen again. Make sure that
Yeah.
you download the table to your computer, okay?
Okay.
To
Okay.
your hard drive, to your computer hard
But
drive.
everything else looks correct, right?
Well, the units, right? The units are missing. You didn't put the units there.
I've put the units for every single one, correct?
Yeah, you gotta put the units for everything.
Wouldn't it just be the meter for each one? A millimeter, I mean, for each one?
Oh, it depends. It depends, right? It depends. What is the share your screen again?
Sorry.
Would be better if I share my screen. What's your group number?
My what?
What's your group number?
It should be hold on here. I think it is one second here. My group number.
Yeah,
I think it's 13 or 11.
13 or 11. Okay, I'm gonna. Oh, 13 or 11. Okay, let me. Interesting.
I can't really open it right now, but
You cannot open it. What you cannot open?
I can't find the hold on, I gotta look for one.
You cannot share your screen, or what's the problem?
I can share screen. Let me share screen. I thought you
Yeah,
want
go
me to
ahead,
see
share your
what group
screen.
number I am.
So you
I
can
can
see.
find what group number I am. Hold on. I can find the group number. Give me a second here.
Mhm.
I'm group number 11. Yeah, I'm group number 11.
Group 11. Okay. So let me
Yeah.
share my screen. Let me share my screen. Okay.
Okay.
Share. That's your spreadsheet. Group 11. Okay.
Okay.
Okay. So you did the significant figures. Okay. Now you have to fill this one here. See that? That's the unit. Okay. This is
Okay.
gonna be diameter, diameter, diameter. What's the unit of diameter?
Meter or millimeter?
Well, yeah, that's right. We use meter, not milliliter, not
Yeah.
millimeter. We are
Yeah.
using just the meter, kilogram, and second. Okay.
So I'll
We're
just
not
put
using
meter on
those.
each one.
Huh?
So I'll just put M on each one.
Yeah.
Okay. And then the ruler, the volume output, M cubed.
Yeah. Cubic meter.
Okay. So that's
That's,
it though, right? And then
yeah.
for
Oh,
the
there is more. Here you go. The slope. What's
yeah,
the
this
unit
one I
of
already did. So I did kg slash M cubed.
Yeah, that's right. And then you need the unit for the different percentage difference as well.
So what's that? How would I find that? What
The
is that?
percentage sign, you just put the
Oh, just
percentage sign
percentage
there.
time?
Yeah,
Okay.
that's a
All right.
unit. Right?
Okay. And then do you have can I see like what the CL min max thing that you said that's on your because
Okay.
I can't see it. Can you
Let
do
me
you have it?
let me get my table here. Uh, let's see. Correction. Where is my table? Oh, schedule, illustration. Is that here? Correction. No. 37, no. No. Let's see if it's not. For some reason, it's not here. What a shame. Petition, blah, 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 blah. You can see my screen, right?
Yeah.
Let me see if it's here. I'm going to make a search here. Nope, not this one. Let's see. Huh. What a shame. I cannot find myself. It must be in the order. That's the problem of keeping things in the cloud, right? When the cloud
Yeah.
fails, we cannot access anything. But I'm quite sure I have it. Why I cannot find it? Or syllables. Posted grades. Syllables. Wow. Let's try it here. What's that? Yeah, okay. That's not what I want. Not this one. It's a PDF file. Huh. Oh man. Let's try something else. I was supposed to find it here in my hard drive. Critical values. Let's put it critical values.
Wait, is
Critical.
it the same one that I saw like it's like a general one on Google? Like I can just search up on Google, it'll be the same one, or is it completely different?
No, mine is better. Mine is better. Mine
Yeah,
was
of course.
designed specifically for this course. Okay.
Uh,
Let's see. I have it here, but the PDF I can't seem to find. If necessary, we use let's go confidence level right in here. Finally I found it. Okay,
mm-hmm.
must be this one. Open file location, confidence level. Okay,
Mm-hmm.
so let me lab reports. Oh, it's on lab reports. I'll copy this guy. Let's make sure that's the one.
Mm-hmm.
Yeah, that's the one, definitely. It is 2024, see? Now let's go to 2025. Oh, here you go. Now, here you go. That's the
Okay.
table that you have to worry about. Okay. That's the
So
table.
how do I use this to do the CL min max?
Yeah, I will walk you through that. Okay.
Okay.
Here you go. N is the number of data points. Okay.
Correct. Yeah.
You're not gonna use this one here. This column here, you're not gonna use. You're gonna
Okay.
use this column, and you're going to use this table here. Okay. This number.
Okay.
This numbers here.
Okay.
Okay, so let's see. Tell me what's the R squared. Let's start with the ruler, right?
Okay.
What's the R squared for the ruler?
0.9798.
Okay, 0.9798, right?
Correct.
0.9798 is between those two numbers, right?
Yeah.
Okay, C rho n equal to 6, right?
Okay.
This whole body that you see here is the R square values. Okay?
Yeah.
All
Okay.
those values, here is the number of data points, N, number of pair. And your CL, your confidence level, is those values right in here.
Okay.
Okay? That's how you should read this table. Let me
Okay.
get my PowerPoint. Here you go. That's how you should read this table.
Okay.
Okay?
Yeah.
And CL, right?
Yeah.
And everything else is R square. Okay?
Okay.
You want to find out what's the CL. You want to find out the numbers here at the top of this table.
Correct.
Okay? And we're going to do that right now. So you said is between 0.94 and 0.98, right? Your R square?
Yeah. Yeah.
Okay. So you want to find the bounds, right? The lower bound and the upper bound, which are the minimum and max values
So
of
that's the minute. Is that the min and max right there?
yeah,
That's low. That's the min and max.
that's right. Wait a minute. The lower bounds and the upper bounds of the CL. Those two numbers are not the CL. Those two numbers are the R square.
Oh yeah, yeah, yeah. Okay, I understand.
Okay?
Yeah. Yeah.
Okay. The CLs are here.
So it'll be 1 minus 10 to the negative 3 is the lower, and then the upper is 1 to the
That's right.
minus 10 to the negative. Okay. So
Yeah.
that's what I would input, correct?
That's what
Like, for
you put.
example,
That's what you
so I would
put.
input, okay. So I would input 1.
It's gonna be like that. You go for the ruler.
Okay, that's okay. I can, okay.
But there is more to it. Okay.
Okay.
You're going to input like that. Equal 1 minus 10 to minus 3. That's how you're going to input. You're gonna put the equal sign there on the left side. Okay.
1 minus 10 to the, wait, you said, okay, so 1 minus 10. How do I put the negative 3 as the as the,
You use the hat. You use the hat. The hat
oh, the
is
how would work?
for the power.
All right.
Hat minus 3. When you put the equal sign on the left side,
So
Excel
I have
does
0.99. I have 0.999.
yeah.
Okay, so I did it right.
And then you do the same for the other one. Equal 1 minus 10 power minus 4. Okay? This number here will always be greater than the other number. The max,
Yeah,
right?
it's
Lower bound,
greater.
the upper
Yeah,
bound
so
will
0.
always be
Okay.
greater than the lower bound.
Okay.
Okay?
Okay.
But you need to have this table. You cannot
Yeah,
use the one in the internet. Okay?
I have a picture from yours now.
Oh, you have? Oh, okay, good.
Yeah,
Let-
okay. Yeah, that's all I need.
let
So then
me-
after that, then that's it, right? And then I'm done. 'Cause I finished
well, you have
everything.
to do for the other ones too, right? Not just for
No,
the
obviously, yeah. I'm gonna do it for
yeah.
the vernicalper and micrometer. Yeah, so the micrometer, it would be, so since 0.9668, the lower would let me see here for the
Uh-huh.
just give me a second here. So it'd be 0.9668. So that would be row
What's the R square again? 0.9?
0.9668.
668. Okay, so it's between those two values too, right?
So it'd be so it'd be 10, so it'd be equals 1 minus 10 to the negative 4 is the min, and then the max would be 1 minus 10 to the negative 5, correct?
Well, wait a minute. You said that's point 0.9 what? 0.96, you said?
0.9668.
Okay,
So
point 0.9,
it would be the row set it would be row 7.
1, 2, row 7. Wait a minute. 0.96. 0.96 is between those two values, right? Between 0.94 and 0.98, right?
0.9668. Yeah. Wait.
Okay, it's between those two values. So the CL is going to be the same CL that we got from the previous for the ruler. Okay, the CL
But
should
it's
be
also between but if you look at row 7, it's also between those two values.
row 7.
Yeah, if you look at the 10, look at the 0.961521, and then right beside it. So yeah, row 7.
0.9. No, 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 no. Here is n equal to 7. You don't use n equal to 7.
Oh, because we're using n equal to 6.
Yeah,
Oh, okay.
you use
Yeah,
n
my
equal
bad.
to
Yeah,
6.
yeah, yeah.
Okay.
Sorry. Yeah, yeah. So it'd be the same thing.
Yeah, it would be the same thing as the other one. It was coincidence. It's coincidence.
So it'd be the same. Okay, then how about the last one? Okay, so since it'll be
Okay,
how about the last
what's that?
0.9895.
Okay, 9895 is between those two values, right?
So the last two. Oh no,
Okay,
wait. 0.98.
okay. So the CL for the micrometer is going to be this one here.
10 to the negative 4, 10 to the negative 5.
Uh-huh.
Okay, perfect. All right, thank you.
Okay.
Yeah, I understand. So 10.
Okay. That's all.
Yeah, that's pretty much it. Thank you.
Okay, well done.
Yep.
Ok, então